Thanks for the invitation and thanks for coming. Batteries are usually considered a very dry topic, okay? So I will see if I can give you some interesting view on that and make it a little more exciting and give you a background. So let's see. Okay, so I really wanted to talk a little bit about, why electrification and give you a brief history of batteries. It's actually rather long, but it does sort of give us a sense of where we've come from. And then what does it take to scale, and then really some of the challenges ahead and kind of what's next, okay? So I am an engineer, but I grew up loving history, and I think history is so important and it informs so much about what we're doing. So there's going to be a lot of historical perspective here. I hope you don't mind, okay? So why electrification? And electrification's been kind of a term people are bringing up right now, and it seems very hot and whatever. It's actually an ongoing trend. We have been doing electrification pretty much since Alexander Graham Bell patented the telephone, right? And that's in the 1870s, right? And and you kind of can watch as electrification sort of picks up steam, as it were, right? So you patent the telephone, and you've got private home electricity in the 1870s where it's starting, and people are starting to say, hey, electricity really works. So, Siemens presents an electric passenger train in the late 1870s in Berlin. And, it didn't occur to me till I was researching for this talk. Electric trains made the subways possible, okay? And the reason that they were popular was because people had long tunnels. And if you were putting a steam or diesel train through a long tunnel, you had to get rid of all that exhaust, right? But with the electric train, then you could suddenly have subways and long tunnels, right? So that's where, London's first electric underground line is put in the 1890s, and that relies on electric trains, right? You've got, power stations, and then, you start getting people getting their home appliances electrified, right? So you get the first washing machines and AC units. The picture on the bottom there, that is actually a steam-driven dynamo. It's in the Henry Ford Museum in Detroit, which is a super cool museum if you've ever in Detroit. I know, it's not usually the vacation spot, right? But a lot of things happen in Detroit. The museum that they have there from Henry Ford has a whole collection of early tools. And you've got early steam engines and early machine tools and some of the stuff that Edison was using and so forth. And it's really fascinating if you're an engineer. So, I've thrown a few photos in of stuff that we did. But that was there to power some of the, generate electricity for a lot of the automaking, right? That, if you're thinking about having a continuous assembly line, you have to have electricity to power it, right? And so he was heavily using electricity early on, right? And then what you've got is, again, more appliances, and then we have a little bit of a pause. There's World War I that happens, right? And lots of things, lots of focus goes to the World Wars. But after that, again, you've got acceleration of development of electrification, right? So Panasonic is founded in 1918 by Mr. Matsushita in Japan after World War I. His first product is really a bicycle light and battery, right? So he starts making little batteries for these bicycle lights, which are kind of a hot commodity in that post-war Japan. And then he proceeded to develop a whole company doing home appliances, electrical appliances for people, right? And it's one of his televisions down at the bottom. But always they were doing batteries since that time. So Panasonic, they're out here at the Tahoe Reno Industrial Center. That's 100 years of battery technology that's culminating in some of these gigafactories, right? A long history. And they've done all the chemistries, right? And then you start seeing, news and entertainment broadcasting, TVs and so forth, really all powered by electrification, okay? And then again, we have another pause. The Great Depression begins, right? And what happens? Well, in Franklin Roosevelt's New Deal, he starts looking as electrification as really important for the country, right? So you've got in the 1930s, Tennessee Valley Authority really looking at providing power to rural south of the United States. You've got the big hydroelectric projects like the Hoover Dam and the Grand Coulee Dam and so forth being constructed as part of the New Deal. And then, of course, World War II begins, right? And actually, electrification, I think, takes off even more. It becomes even more important because we, in the United States, are building all the armaments for fighting World War II, right? So power becomes a huge issue, and electric power becomes a huge issue. So that really, by the end of the war, 90% of US households are connected to electricity, right? And then, as you kind of see going into, the more modern day, right? You've got things like the high-speed trains, the Shinkansen in Japan. You've got, in 1970s, you've got solar panels that are only used for the most exotic application, satellites, right? But that's where, solar panels were very space age, okay? And, some of us remember that, Jimmy Carter put solar panels on the White House lawn. Well, and that was an area of criticism. I knew Ronald Reagan hated them, pulled them all out. But at the same time, he was basically demonstrating a very space-age technology at the time, which was about electric power, right? And then, you've got the computer age really dawning where, suddenly everyone's buying computers, and that's coming in. And again, it's just massive electrification. We use more and more power. And of course, as we're looking at AI now, that's even more power hungry, right? So electrification is not a new thing. It's an ongoing trend. It's been going on for 150 years, and we are just accelerating into more electrification, right? So, why electrification? Well, okay. People really find that electrification, it just creates the better user experience, okay? Every time you electrify a sector, people find that the electric versions of whatever it is are way better, okay? And you're first like, well, really? And then like, yeah, really. Because you really want electric lights in your house, not candles, okay? All your home heating, cooling, all those appliances, more and more electric, more and more easy to deal with. All the entertainment issues, your manufacturing capability gets better when you have lots of electric power. Electric trains versus steam and diesel, I spend a bunch of my time on the peninsula and in the Bay Area. Just got the electric trains on Caltrain, replacing the diesel engines, and the whole community feels the difference because the diesel engines were loud, and so even if you were miles away, you heard the diesel coming through. The electric trains are quiet, they don't smell bad, and they can accelerate and decelerate faster, so Caltrain was able to put more trains on the line, and so now the train comes every 30 minutes instead of every hour, right? So from a community experience, it's like, this is awesome, right? And you've got modern EVs with now suddenly infotainment. Like when I was growing up, you never talked about the infotainment system in your car, but that is what people call, that big screen that Tesla has is considered infotainment. And, in the US, we're like just getting used to those screens, right? But the folks in China have been making EVs that now have all these feature-rich, things like big screens in the back seats for the people sitting in the back, and massage chairs, not just heated seats, right? All that stuff becomes possible with an electric car. It's not really possible with an ICE engine unless you put a big 12-volt battery or big 48-volt battery in there. And all the autonomous driving takes a lot of computing power. You don't really get good autonomous driving if you're going to be in an ICE engine car. So all of that, push really relies on electrification, right? And then, like solar power and batteries versus diesel generators, right? Maintaining a diesel generator, it's a bit of work, right? And most people are like, wow, that's inconvenient. I'm not buying one for my house, okay? But putting solar and, backup batteries on your house, real easy, okay? And, I have a place up in Somerset and the wind comes up and sometimes NV Energy will shut down power. Yeah, it's real easy when you have solar plus a battery backup. You don't even notice, right? You're like, we're good, right? But it's convenient. I'm not out there changing the oil on my diesel generator, cranking it up every, once a month to make sure it's working and the whole thing. So super convenient, super easy. That's why people do electrification. And I brought a prop. I brought a demo. So, we talk about electrification. And I wasn't sure if people would recognize this, so forgive me. So this is my electric iron, okay? I wasn't sure if the students knew what electric iron was, okay? But you know, this is a very nice electric iron. It's got lots of nice features. It's got steam. I can set the temperature. This is great. This is the predecessor, okay? This is how you used to iron stuff. You put this on a hot stovetop and you let it get hot and then you kind of iron it. I'll pass these around if you want to. Well, let me pass these around. I'll send one this way. And for those that don't remember what these things are, and you've had a modern iron, you're like, yeah, right? Okay. But this is kind of, you know, this is why like electrification is a trend, and everyone really actually, you know, we like electrified products actually, all right? Regardless about how, you know, people are having disagreements about, you know, do they want to run big trucks or IC engines or what? But the truth is, you know, once you try the electrified products, you're like, wow, this is really good, right? So, you know, that's one of the reasons about why electrification. But the other thing is, I want to say is, why electrification now? So first off, I mean, this is not a new thing, okay? This is a trend that's been accelerating for 150 years, all right? We are electrifying one segment of our society after another all the time, okay? Why now? Well, Tesla did many things, but the one thing it did was prove that lithium-ion based batteries were good enough for cars, good enough for ESS, and also that they could make aspirational products, okay? Before, you know, Tesla really debuted the Roadster and the Model S, you know, you talk to people about electric cars and they were like, golf cart, right? Glorified golf cart, it's going to be miserable experience. That was the expectation. And it's true because, you know, I was in grad school in the 90s, right? I was at Princeton and I was a mechanical engineer, but associated with the engineering department was the Center for Energy and Environment, okay? And there were a few professors there and some grad students, and they really spent a lot of time telling you about climate change, and, you know, it was really depressing to talk with them, right? Because they're talking about climate change and you're like, oh God, really? I mean, I was raised Catholic, I have enough guilt, you know? And it's like, these guys make me feel, you know, they make you feel guilty. And then they would also like do these paper studies about cars with like fuel cells and fuel cell cars, and they never had the guts to actually go buy a car and try to outfit it with a fuel cell. It was all like paper studies, which I found really unimpressive, you know? It's just like really, and they were so earnest about this stuff, and you're just like, oh, no, you know, I don't even want to think about it. And, you know, and that was people's view, that this is what an electric car was going to be, until the Model S showed up and people realized that they had, you know, they had a sports car's acceleration with room for 5 and all the groceries, right? It was like a completely different world. And, you know, I took the ladies that I was singing with at church, you know, and I was by far the youngest there. A lot of them were in their 70s and 80s. We went joyriding in my Model S when we got it. And it was like, this is awesome. Like, it was like super clear it was better, right? So, you know, what we're seeing is, okay, we can do this, right? And it's not going to be miserable. It's not going to be freezing in the dark, right? It's going to be, you know, electrification can be completely better, right? And, you know, that's what these cars proved. That's what Tesla showed. And then, of course, climate change has been occurring. I didn't want to believe it when I was in grad school. I was like, God, I hope they're just nuts. I just really hope they're nuts, right? And then, you know, kind of started working. I was at Exponent, and we had our scientists do a study, look at, you know, climate change, is it real, evaluate the science, take a look at it, and give us a talk, and they did. And they said, well, you know, yeah, this is happening, and what the other thing you don't know about at that time was there'll be a lot more extreme weather that's happening, right? And so now we're seeing the extreme weather, and it's impacting a lot of people that didn't think they were going to be impacted by sea level rise, or, you know, weren't worried about it because, well, whatever, that's going to happen. You know, maybe we'll lose a few Pacific islands, but we live up in the mountains, that's okay. And now suddenly we're talking about extreme weather, right? And whether you choose to believe in climate change or not, the reality is most of the rest of the world does, okay? The folks sitting in London, and I was in London this summer, and it was hot, like not what London should be, okay? They don't have air conditioning in their houses, and they're sitting in these houses, and they're getting hot, And what's worse is that subway system that was always like the pride of London, it's overheating now. And so you see signs on the London trains that say, if you're feeling woozy or, ill, sit down, ask for help, get some water, right? Because it is now a heat stroke issue for them. People like that, they're losing patience, okay? They're saying, okay, climate change is a real thing because it's affecting me, and we better change that, right? To the point where, like today I was reading in Bloomberg, right, that BlackRock, big hedge fund, funds a lot of stuff, their European pension fund members are pulling money out of BlackRock because folks that are investing their pension funds in Europe are saying BlackRock is not focusing enough on sustainability questions. Okay, and of course Bloomberg points out this gets a little tricky in the US where talking about climate change causes other, puts you out of favor with certain part of the United States, but in Europe, not talking about climate change is putting you out of favor with folks there. So people are starting to pull their money out because we're not talking about sustainability enough. You can envision a place in time where people will start looking at the U.S. and saying, that, CO2 emission rate, you guys keep increasing? Yeah, we don't like that, we're gonna sanction you. And that's something that, like, as an American, no one sanctions the U.S., right? Well, the world's changing, right? And do we run that risk, right? So that's, whether you believe in climate change or not, doesn't matter so much because everyone else does, and they're gonna act accordingly. The other thing that's really important to understand is that electrification changes the geopolitical order, okay? When you're in a petrochemical world and a gasoline-driven world, it's all about who produces petrochemicals. When you're in an electrified world, it's all about who manufactures batteries, okay? And all the raw materials for batteries. So the Chinese have been very, very logical about this, okay? They have decided they want to be a world power. They're going to get there through economics. They have embraced electrification and EVs as the way to become an automaker, which is a huge industry. And they've said, we're going to be an automaker. It's going to be electric because we can't compete with ICE engines and we don't have a big petrochemical background. So we're going to do electric cars. And they have pursued this over the last decade, deciding to be, fully vertically integrated, deal with the raw materials, the cell making, the auto making. And, they are being very successful about this. And they also know that as the world shifts to electrification, they get the economic power because they have the rare earth magnets that, make the electric motors. They have all the raw materials to make all the batteries. They've got the cell makers, they've got the car makers. So it changes the geopolitical order. And we need to realize that and where we are versus that, okay? And then, they said a decade ago a Made in China 2025 policy, and they are producing so many batteries that they can supply a lot of electrification. So this is why now this is important, because we didn't think we were in a race, but we are in a race to maintain, our position in the world order, okay? So, with that, I want to talk about batteries, okay? And again, I like history, so I want to give a very brief history of batteries, okay? And forgive me for the scientists in the room who know this, like, backwards and forwards. But, so, where do batteries start? Well, the first term electricity battery was coined by Ben Franklin, okay? He was thinking of some of the military batteries that he had, and he was playing with lightning, so I guess the ideas came to mind together. What he was doing was he was using something called a Lyten jar. And a Lyten jar is basically a glass jar, and it's got a metal foil on the inside and a different metal foil on the outside. And you put a conductor down into it to touch that metal foil, and you might fill it with water to make things better. And what you can do is you can store electricity in that. And basically it's a big old-fashioned capacitor, okay? So it's a high voltage device, and what Franklin was doing with that kite experiment was he was trying to show that the electricity, the thing in lightning, that was electricity, and that people were playing with electricity with static discharges and dynamos and stuff, and he was showing, it's the same thing, right? So he wanted to collect some of this. So he flies the kite into the storm, He does not have the kite struck by lightning. People think he would have died if it actually been struck by lightning. But basically, he's up into the clouds where there's enough electric charge, and then he's got this key connected to a Leyden jar, and he's collecting current in this thing, right? And there are various depictions of this. I found like 3 different depictions of Ben Franklin. I'm particularly enamored with the cherubs, right? Like the very classical thing, but he's got the key and the string, and he put his knuckle up to the key and he could feel the static discharge, and so he knew he was collecting stuff. The diagram of what was actually happening is that he and his son were sitting under a shed holding onto a silk rope that was dry, which was connected to a wet rope, a hemp rope that was conductive and flying the kite. And then the key was connected to the Leyden jar, and he was collecting charge. And then he was like super pleased that he got, he collected electricity and was able to discharge this thing, and it was a big deal. So that was like the 1700s, 1750s, right? Okay, great. 50 years later, people are messing around with electricity. Volta actually creates the first real battery, okay? And what it is, it's a bunch of stacked plates. It's like copper and zinc plates, and there's some like fabric in between with a brine in it that's the electrolyte. And it's called a voltapile, and it works. It produces a stable current. Not for very long, okay? But it produces a stable current, tends to short circuit. It's not a very useful battery, but it's useful enough to be a research tool, all right? And so this became a scientific tool, and people used it to actually isolate a lot of elements, right? Because they used it to produce electricity and do electrolysis and so forth, right? So, okay, that's 1800, okay? Now, 1859, again, 60 years later, Gaston Plante creates the first lead-acid battery, okay? And this is, he has 2 lead strips, and he has some rubber in between, and he puts them in sulfuric acid. And this is really the first rechargeable battery, okay, that people have, because you can charge it and discharge it. Not super useful, like they could light up train carriages and when they stopped at a station, right? It was a little tough to build, okay, because you had to do some interesting things to get the materials active, whatever. But basically, it's the same chemistry that are in the lead-acid batteries today. You've got a lead plate, you've got a lead oxide plate. In sulfuric acid, when you discharge the thing, you make lead sulfate and water, and when you charge it again, the sulfur goes back into solution. You have hydrochloric acid, and you have lead and lead oxide, right? So it wasn't easy to build, but in 1881, right, about 10 years later, Camille Fauré improves the design, right? He gets a lead grid lattice, and then he presses the oxide onto that lattice, and you can cure that thing, and you can, and then you cure this thing, and then you make these kind of plate batteries, right? That design is really what our lead-acid batteries today look like, okay? And they're still used. And I wanted to show some videos. Oh, before that, okay. So where did we use these things? Well, so these were the original cars. There was a whole set of electric cars, okay? So Ford was off making Model T and aiming for internal combustion, but there were other automakers who were really doing this, making electric cars, because they were, again, more convenient and easier to drive. You didn't have to crank the engine, okay? Now, the Model T finally won out. The internal combustion engines won out because if you were going to go take your car out into the rural burbs, you were going to be hard-pressed to find any place to recharge it, okay? So it wasn't charging infrastructure. And once someone developed an electric starter, and so you didn't have to go crank on this stuff, internal combustion engines became easy for people to use, and they could throw a few extra tanks, cans of gas in the back to be able to go longer distances. But before that, electricity was considered the nicer car, and you had a lot of taxi fleets in the big cities, and they had swap stations for their batteries, right? So that's where a lot of the lead acid was. And then something people don't remember is that the U-boats in World War II, the Germans, these were diesel engine powered submarines, and they were mostly on the surface, and they might have a snorkel, but when they dove, they relied on lead acid batteries. okay, to power them. Produced by the predecessor of Varta, which is still a company that's around making batteries, right? And they were basically making these for 40 years during the war, and they were the Allies underestimated the importance of batteries. This factory was kind of on a list of things to bomb, right? And the British were having terrible trouble with U-boats because they were destroying the merchant shipping fleets, and somehow no one figured out to bomb the battery factory, okay? Because it just wasn't sexy enough, I guess, right? Right. And we still use these batteries for like I said, our cars, including the original Model S. The way the car was set up was that it stayed awake because there was a lead acid battery there. Okay, Tesla's since moved on, but very workhorse battery, works great at low temperature, can deliver a hell of a current for you. That's why I can turn an engine over. Still use and still going to be using. The other thing to keep in mind is that the phone companies used the lead acid batteries forever as the backup for their phone lines. So when you had a landline, you noticed it had its own power. That's because the phone company had a big battery backup system in every town. And usually the building would be some low-slung building built out of cinder blocks with almost no windows, somewhere innocuous around town with AT&T on it. That was their battery backup. They'd have a room full of lead acids that they would be maintaining. Okay, they're currently still use lead acid, trying to move to lithium-ion. Okay, all right. So I want to show these videos because this is how a lead acid battery is made, and this is currently in India, I think, and that's lead oxide, and they're putting it in a mixer, adding water, adding the other stuff that they're doing, right? And they make a nice oxide paste, and the lack of PPE is horrifying, right? You're watching this, you're like, oh my God, this is lead. Okay, and this is lead, okay? This guy's got a book mold, right? And he's taking a ladle and he's pouring lead into the book mold and, making the grids, right? And again, you're horrified, there's no PPE here, and these guys are in sandals, right? And, but this is how lead acid batteries were made, I think, for a long time. I mean, if you're looking at this, they're coming from the 1860s, okay? This is not real different from how people do it. And then this is them pasting that oxide paste onto the battery, right? With a spatula, okay? And, and then they're drying them out, calendaring them to make them flat. Huh? The newspaper's fantastic. Yeah, it's your, consumable, right, in your factory, right? Okay. That's how you would make these plates. And, this is not fancy manufacturing, okay? And you can tell this is not a particularly precision operation, but this makes very workable lead acid batteries, which is why these things have been a workhorse for, our society for a long time, okay? And, I was in Korea when I was at Tesla. We had, those 12-volt batteries, and I had to find a source because there was drama there. Anyway, so, went out to see a bunch of Korean factories, right? And I saw, with my colleague, the full range. We saw something that was almost like this factory, where we walked in and the guys, they had a rotating mold for the grids, but for all the extra hardware that goes on, the straps that go between the plates, they were literally using kitchen ladles, pouring the lead out and molding this stuff with kitchen ladles, right? And putting this stuff together by hand, okay? And then we went to a much more advanced factory where they were doing, they had really optimized how they do high-speed production, okay? But what you would see in a modern factory is you would see that processes are automated. People don't touch the plates anymore, okay? The lead is formed into strips on rolls, and then the rolls are sent through, they're somewhat, these big rolls, and they have the lead wrapped on them, and they'll take that through a machine that will laser cut or punch a grid into it, and then expand the grid. So they're not even punching out the holes. They're making a pattern, and then lead, because it's super ductile, they can just expand it and make their pattern for these grids, and then it'll automatically just paste in all the lead oxide and then chop up the plates, and then, they have automated systems that will drop these things into into stacks and then cure them and pull them out, right? A completely different approach, but it's the same type of chemistry that you can make by hand like that, right? Of course, the performance is somewhat different. That stuff you make by hand is going to be a little sketchy, okay? It's not going to give you the lifetime, but it works, and that's what drove really a lot of our industry. It was lead acid batteries. Okay, all right. Just wanted to touch on alkalines because we all know and love alkaline batteries, right? This is what we used in flashlights since I was a kid, right? So these things were really they started with magnesium dioxide cathode, and that's still used, whether any of these cells, and then the early ones they did a zinc foil anode. And they started with ammonium chloride, and it was not a great cell. They used it to power early telephones, and there was a picture of that telephone that had 2 batteries in it. That's what the Leclanché cell was. But they just before the 1900s, National Carbon created this zinc carbon battery, and it's a primary cell. It's still made. Zinc carbon batteries are still made. In a lot of Europe, there'll be factories that do this. They're very cheap. And because they were so cheap, people could buy them, and this is also what led to the flashlight invention, right? So, coming out of the 1800s. And then finally, it was only about 1960 that the common alkaline battery that we use today really became a thing, right? And that was developed to use alkaline to KOH electrolyte. It's considered an improvement for zinc carbon. Zinc carbon battery is really susceptible to the battery using up all the zinc and then leaking because use the zinc as a case, right? The current alkalines don't tend to do that as much, right? Okay, so then I want to talk about, the other thing I want to point out here. So that cylindrical form factor, right? We came out of the lead acid batteries and you're using plates, right? And the square. So for alkaline batteries, these are I think they're called bobbin cells, right? You've got, let's see, this works. So you've got, your electrode is basically you've got the, center pin, and then you've got a bunch of stuff around it, okay? Those are your 2 electrodes. They're very simple design, but they are cylindrical cell. And, all these cap assemblies and stuff, that's how people learn to put these batteries together. You see their derivatives in the current lithium-ion cells, okay? The people that were making these were people that later on started making lithium-ion batteries, right? And they started borrowing from those technologies that they had to make primary cells, right? And NiCad, this thing was, again, early made in Sweden, was commercialized in Sweden, but not unknown in the US until after World War II. Then it was brought here. They were a lot like lead acids, rechargeable and nice, more robust. They're also way more expensive, right? But later on, what people were using these for was these were the small rechargeable cells that people were using for, toys and power tools and other stuff, also in the satellites, right? And they actually introduced the spiral wound jelly roll structure, which is really what makes lithium-ion cells, right, work. So that's what, that's another thing where people were making NiCads and they borrowed that technology later on to make lithium-ion cells, right? Okay. Nickel hydrogen is fun and interesting because this is what the US finally went to for all their satellites and their space programs. So the first batteries on the International Space Station were nickel hydrogen, so was the Hubble Space Telescope and a whole bunch of satellites. And this one was like a nickel cathode and then high pressure hydrogen, right? So the literature says 1200 psi. When I've talked to people who were in the business at the time, they were like, yeah, the ISS batteries, we've kind of topped them up with about 5,000 psi of hydrogen. And I was doing a project with them to replace them with lithium-ion because they'd kind of come to the end of their service life. And they're like, yeah, we don't quite know how we're going to return these to ground with 5,000 psi of hydrogen. Maybe we should let them burn up on reentry, right? But these were like workhorses, and it was a weird technology because you had to have a pressure vessel, right? Kind of simple to make, but like not really practical for small stuff. So it kind of disappeared, right? Until about, 5-6 years ago, out of Stanford, there's a group, Yi Shui started a business to try and make nickel hydrogen for stationary. And this company called Intervenue started doing this, and they were like, hey, these batteries are super easy to build, okay? You just have to make a tank, okay? And you build the thing, and they've got a business making stationary battery packs. They had a factory in San Jose. They've currently moved it to China. Why? Because the Chinese offered them free land and a bunch of money to come and manufacture in China. And I talked to the CEO. He lives a few doors down from us in San Carlos, and he's like, yeah, I couldn't find a way. He's like, there was no way we could refuse that offer for the business, because there was like the land, the money, and then they gave us a shell of a factory. And we walked in it, and there was like this much dust on the floor, right? And it was terrible. And then 12 weeks later, it was cleaned up with our tools dropped in, and we were ready to make batteries, right? So they are doing this right now, and that's one of their units. Okay? All right. So nickel hydrogen, like, wasn't practical for small stuff, so people started doing nickel metal hydride, okay? And then there was drama, okay? So if anyone has seen Who Killed the Electric Car, nickel metal hydride features prominently in this, right? So, you know, technology is invented, and there's a company called Ovonics out of Stanford, and they begin working on this, and you know, nickel metal hydride enters the consumer market. That's currently what you get for rechargeable stuff, like, you know. They usually look sort of like that, right? That's nickel metal hydride cells. I have them because I have a few solar lights, and then when your solar light battery goes bad, you open it up and you go, huh, I got to go buy a replacement from Amazon. That's a nickel metal hydride cell, right? But anyway, so that's going okay, right? And then there's this consortium USABC that starts, and that was GM, Ford, and Chrysler. And they started looking at, you know, electric cars, right? And the allegations from the guys from Ovonics are that these guys really were just slowing down electric cars in the US, right? That's their allegation. They're like, those guys were just, and I'm like, huh, you know, really? Conspiracy theory? You know, because I've seen some of the stuff USABC does, and they've put a lot of nice standards out for, you know, how do you know a battery's good for a car and everything else. But you know what? They also sandbag stuff. They'll say like, oh, you need the super high energy density before Americans will buy electric cars. And I'm like, huh, I got 2 Teslas sitting in the driveway, and they don't have nearly that energy density of cells, and they make good electric cars, and you know like they have this tendency to be like slow rolling stuff, right? So I don't know, maybe there's something to the conspiracy, but whatever. And then like GM acquired a bunch of this company. They were going to use this for EV1, and then Texaco purchased that company, the shares from that company, right? And then Chevron purchased Texaco, and then basically like Chevron files this patent infringement case against Toyota and Panasonic because they're making nickel metal hydride for a RAV4 electric. And like the settlement was really interesting because Panasonic Toyota couldn't use large nickel metal hydride batteries for non-plug-ins, like for plug-in vehicles. They could still use them for the Prius, it wasn't a plug-in, but they couldn't make plug-in hybrids or, you know, plug-in electric vehicles with large nickel metal hydride. And that continued in force until 2010, right? And at that point in 2010, lithium-ion batteries were already a thing. The Roadster came out in 2008, right? So, you know, I hate to say this, but in the US, we had a chance to be the leaders on the electric car, and we kind of squished it, okay? And, you know, you can be like, wow, that's a big conspiracy theory, but when you look at it, you're like, wow, we kind of blew it. We could have been way in the lead, but okay. So we got another round at this with lithium-ion, right? So lithium-ion again, so there's 3 names, right? The guys that won the Nobel Prize, Whittingham, Goodenough, and Yoshino. Okay, they figured out different pieces of the lithium-ion battery. And, you know, lithium-ion battery is an intercalation cathode, which is different than lead acid. And it has to do with the lithium actually just inserting itself in the crystal structures of the cathode, and then again on the graphite side, it inserts itself into the graphite. It doesn't react with the graphite or with the cathode. Lead acid, you've got a chemical reaction happening. Lithium sulfur, you have a chemical reaction happening. Lithium-ion's different. They call it a rocking chair battery, or they call it intercalation battery, because that's what it does. So it's really different, okay? It's a really different technology than everything else we've seen, okay? So those guys go and they over time develop this battery, and Sony commercialized in 1991, okay? And they did it first for camcorders, okay? They did not commercialize this because they wanted to make a new battery. They commercialized this because they wanted to make camcorders and sell camcorders. And because they were super power hungry, they needed a better battery, okay? And then they started putting these in laptops, which are also super power hungry, okay? And you know, this started going well. And the price on these batteries, the first ones, it was like $50 a cell was for the camcorder, which runs out about $6,000 a kilowatt hour, okay? Anyone know what the current price, typical price is for lithium-ion cells?
150.
Yeah, it's about right. It's about 150, right? And you can see the curve drop out there. That drops in the earlier 2000s to about 200, right? But these things were expensive, right? But they were really good. So, you know, so lots of people start jumping in on this, okay? You've got Chinese guys doing it. You've got LG and others jumping in to make this stuff. Batteries are going into laptops. Everything's going good, and then, you know, batteries start catching fire, and you get those videos, right? And then in 2006, Sony recalls about 10 million battery packs. And the word is in that recall, they lost all the profits that they had made on batteries up till then, okay? And Sony never really recovered. They sold off the business to Murata. They don't make cells anymore. But, you know, you still had Panasonic and Sanyo, and then Sanyo and Panasonic merged, right? Okay. Now, what happens in about 2003 is that Tesla's founded by a bunch of guys who decide they want to make really badass sports cars and get babes, okay? That was actually like their thinking, right? They were going to have sports cars, they were going to be electric, they were going to be awesome, they were going to be the talk of the town. That's, Eberhard and Terpening, right? The early founders. And then, you know, basically Elon took in because he was funding this thing, and then he took over as, you know, as adult supervision, as it were, okay? You know, they built a Roadster, and finally in 2008 they built a Roadster, right? And it proves that, you know, these cells can make, you know, laptop cells can do a car. And, you know, Tesla at that point, one of the things that was genius about Elon was that he wasn't interested in making a sports car, not really. He wanted to make a mass market car, okay? The sports car for him was not the end-all reason. He wanted the sports car to fund a good sedan, to fund a mass market vehicle. That was the Tesla master plan, the first one, right? So that's what they did, right? And, you know, they got a big loan from the US DOE. This is the Loan Program Office. At the same time, Tesla got the loan and Solyndra got the loan. And Solyndra is like 2 blocks from the Tesla factory, Fremont factory, okay? And Tesla succeeded and Solyndra went down. And, you know, a lot of people made hay about Solyndra, and they forgot the fact that at that same loan program created Tesla, right? And, you know, it's like, well, you win some and you lose some, but people really get irritated about that, right? Anyway, so, you know, Tesla makes this car, and we won, and I was there, and we won Motor Trend Car of the Year, like, first time out, okay? And you're like, really? New startup company, never made a car before, wins Motor Trend Car of the Year? Like, the Roadster was like 2,000 cars. Model S was making this stuff. And it, you know, it goes to tell you that the electric car made making a car easier, so you could be better in every category, right? So it had that infotainment system, like all those electronics. It looked like a phone on a, you know, on a chassis. Well, okay, so you had that, and then you had the better safety and everything else, right? And so, you know, so the car won because it was just so different than everything else, and so completely different to drive, right? And, you know, and that's the thing, is that when you went electric, it opened up a whole different space of vehicles, right? And made them just completely different, right? So, you know, things went on. You know, Tesla broke ground in Nevada, and the picture on the bottom is you know, those were the dirt movers. Like, I went up there and like, wow, okay, there's a lot of dirt, okay? You know, it's no factory, right? But, company put up the factory, worked with Panasonic, about a $6 billion investment between the two companies to build that factory. And, about 2017, which is out here, they produced their first cell, right? It took a while, though. It was 2019 before Panasonic was profitable up there, right? Because you had to just ramp this factory, right? Now, meantime, this is happening here, but, CATL, the big Chinese battery makers, founded in about 2011, and, BYD is there, and they're also making batteries, making cells, and starting to make cars. And in 2023, BYD surpassed Tesla in volumes, right? Okay, so why is that? And I thought about what it takes to scale, and I am an engineer and not a finance person and not an economist, okay, even though I like this stuff. So I think as a chemist or a chemical reactions person, and I always think, you think about activation energy, you want to go reactants to products. Well, you don't go in a straight line to products, you have to go over that activation energy hump, right? And you can think about scaling as the same thing, right? You can look at, okay, I have a choice. Do I scale? Do I not scale? I'm looking at the profits that I could make after scaling. That looks good. But then I've got this whole cost to scale, right? And I can, there are various things that could make that cheaper. They could be catalysts for me for my scaling process. But, what does this look like? So, all right, so, what does this look like? Well, profit after scaling, it's going to be dependent a lot on product demand, my cost of materials, my cost of labor, right? The whole thing about the factory, okay? What's my cost to scale? Well, I'm going to have a cost of financing because these numbers to scale are big, right? So somehow I've got to borrow the money or I've got to do an IPO or something. I got to purchase land, I got to permit it, make sure all the utilities are out there because, again, making cells is a power-hungry endeavor. You've got to have plenty of power, right? I've got a whole number of things that are going to cost me to scale. And this is something where, for students, you go and you say, oh, I want to build this project, or I want to do something in a factory, or I want to propose a project. And you always you think about that profit after scaling, the profit after you do the thing, and you're like, oh, it looks really good, right? And a lot of people forget that, well, to get to that profit, first you're going to go over that activation energy. It's going to cost you a lot of money to get there. And all that time, after profit, right, all the profit here, that's got to pay for all this, right? And you've got to think about both things. And then you think about, well, what's going to catalyze this? What's going to happen? How do I make this happen faster? And that's where the government comes in, right? What are they going to do to make this go faster, right? You can provide financing, you can try to do incentives, land grants, whatever. There's a lot of things that can make this easier, right? So, and I looked and I said, well, what's an example of fast scaling in the US, right? Have we done it before? And we have, okay? I just finished reading this book, Freedom's Forge, which talks about how the US mobilized in World War II, right? Because at the time, the US was coming out of the Depression. They were making things in the US, but not a lot of them, okay? Industrial production was way down, and it was not nearly enough to support a war effort, okay? Shockingly not enough. It's amazing that the US actually got it done. But what happened in there, and it's a really fun read, it talks a lot about the big companies and how the government sort of catalyzed fast scaling, okay? And a couple things come through. One is that they really ensured that the manufacturers had profits, okay? Which created a lot of heartburn for a lot of people, right? The new dealers hated this, but the guys who were doing this were like, the manufacturers got to have profits, otherwise they're not going to do anything, right? So they made sure they had profits. They also, limited non-military production, so, you couldn't be going around and making refrigerators and making a killing on refrigerators while your buddies were out there busting ass making tanks, okay? So government did some stuff. They also encouraged cooperation, which in today's world you would call that monopolistic practices, or you call that collusion, right? But the reality was that multiple companies were making the same engines, the same aircraft, and they were trading back and forth best know-how and helping each other out with supply chain and other stuff, which today would be considered completely non-competitive. But it was important for making this happen. And the government did things like they rationed key materials. If you wanted rubber, you better be making something for the military, otherwise you weren't getting it, right? But they didn't micromanage production. They gave lots of money to the big companies because they said they have the engineering talent to do this. We're going to let them do that. We're going to put the orders in, right? They'll work out with the subs who's doing what, right? And then they did give some newcomers a chance when there were big gaps, right? So the classic example of this was Henry Kaiser at the Kaiser shipyards, who built the Liberty ships, right? And there's a new national monument. You go out the Rosie the Riveter National Monument down in Richmond in California. Fun place to visit. They have the pictures of what these shipyards look like, and one of the Liberty ships down there. And these things, the guy had never made ships. He was actually a construction guy. He built roads, he built the Hoover Dam, the Cooley Dam, but the merchant marine vessels were not available. And the British needed them, and the British were willing to pay. And the US shipyards were all full up with orders from the US military. So the US government said, all right, Henry Kaiser, we'll let you build ships for the British, right? He went down and he started building these Liberty ships and figured out how to do it in a mass production way. So that by the, usually a ship would take like over 3 months to build, 4 months to build. And he got it down standard to like 39 days to build a ship, keel to the top, right? And then he was competing. He had one son running a shipyard, a similar shipyard in Washington State, and his guy also running the Richmond shipyard, and they were competing for the record of who could build a ship fastest. They got it down to 4 days and 15 hours. That was the fastest ship, keel to top, right? And he did this by doing this mass production approach, pre-building a lot of the components and stuff. Super fun to read. I recommend the book, right? All right, so how are we going to scale cell making, right? Because people talk about this, national security is really important, right? Okay, so some numbers here. Nevada Giga, the CapEx was $6 billion. People in construction, like you talk to McKinsey or you talk to construction guys, they'll tell you it's about $100 million per gigawatt hour if you scale the factory, about. And then you need about 150 people per gigawatt hour. Now, people have talked about getting this number down. There was this big thing that you're going to do lights out factories. Northvolt was supposed to be in northern Sweden, was supposed to be a lights out factory, okay? You were like, why the hell did you put it there? There are no workers. Well, it was very fashionable at that time to think you could do it with almost no workers, okay? That was, it turns out it's harder than you think, right? It took about 2 to 3 years to achieve full production once all the tools and stuff came in there. If you look at this, it's about 5 years to profitability, okay? That is a lot of time and a lot of raw materials and a lot of cash that you need to get this happening, right? And I gave some comparisons. So QuantumScape in their IPO raised about $1.4 billion. That ain't gonna build you a big giant factory, okay? Northvolt raised $13 billion, but they kind of tried to get really big, okay? And they did a lot of things and they never managed to get it to happen. When we had the Inflation Reduction Act, they set aside about $3 billion to support US manufacturing and grants, okay? That's like half a gigafactory, right? And they tried to spread this like peanut butter into various, offer grants to people, right? And I went for that grant, and the biggest grant I could try to aim for was $300 million. And I would have to raise another $300 million to be qualified for that grant, right? And it was still not gonna get me close to a factory, okay? So, it was like, it's nice, but, people think $3 billion is a lot. Half a gigafactory, okay? The thing that actually made a big difference in the IRA is this 45X tax credit. So you mentioned cells are running about $150 a kilowatt hour. So you got a tax credit of $35 a kilowatt hour for cells. Now you can take that and be like, okay, I can build some factories. And that's why you have Panasonic building another factory in Kansas. That's why you have SK and the Blue Oval and all these other people rushed to actually build factories in the US, okay? This bit, super big catalyst. This bit, not so much, right? So it's kind of a, if we want to scale, this is the stuff we have to think about, right? So, why is the cell making so hard and so expensive? Well, part of it is there are a lot of processes in a cell factory. That lead acid battery factory looks super easy, right? And it is, Okay, that's why we had them since the 1800s. A lithium-ion cell is like high precision. There's, a whole thing about electrode making, and, the coating machines are like, a football field in length. They're complicated. Things move fast. You've got to have all this precision. And then you have to have all your raw materials coming in also that are super engineered and high precision, right? So you're doing super CapEx intensive. Stuff's moving really fast, okay? And then the assembly lines are really complex too. And they're, it's tough to find a clear picture of a winding machine. That's a winding machine. The job of that winding machine is to make a jelly roll. That's a jelly roll sitting in a can. This is a very vintage jelly roll, okay? This is from like 2013, okay? They're nicer now, but you can see this is a lot of reps, and it's going really fast. It's going faster than you can see, and it's tough to keep it all aligned and everything perfect, right? It's a pain in the ass to maintain this thing, okay? So basically, to have really good performance out of a winding machine, you get a crew of cleaners on there once a week or every 2 weeks with Q-tips, cleaning all the little sensors and all the little rollers, because they get dirty. There's a lot of material running through that thing, and it just rubs off and gets dusty and everything. So, trying to run that, and you might, like Panasonic has somewhere north of 200 winding machines sitting on the floor at the Gigafactory here, right? So you've got these super complex machines, and then you've got multiple different processes that happen in sequence. So it's super easy to either bottleneck or starve your production line and not get the utility out of it, right? Okay. And you need a lot of controls engineers because there's a lot of data running back and forth, and just to keep the line moving. And we're not really good at training controls engineers out of universities. We do control theory, which is great, but it's real different to do practical controls engineering. Most people learn it on the job, and like the highest paid engineers in the factory are the controls engineers, okay? Like they're worth gold if they're good, right? So, and then the other thing, this is what like trips up the automakers. Like all the automakers, they became really fashionable. All the automakers are gonna make their own cells, okay? They were like, Tesla's gonna make their own cells, VW's gonna make their own cells, GM's gonna make their own cells, everyone's gonna make their own cells. Well, and they're like, we're good at manufacturing. We surely can make our own cells, okay? The automakers are good at manufacturing cars, okay? The thing that's this trick about car manufacturing is you've got to bring all the components to the factory at the right time and the right place, and you got to put it together. So car making is all about the logistics, the part logistics, right? And if you're missing a part on a car, your line's going to stop till you get that part, right? So that's the magic of car making, is logistics. That is not the magic of cell making. Cell making, the raw materials you send into that factory are pretty limited. You got some powders, you got some current collectors, some separators, some cans, a few tapes and tabs, right? Your number of components, your components list is real small. What's tricky about cell making is it's super high speed, so super short takt times. So you're talking of fraction seconds when a cell is in a tool, okay? Because it's super automated. And yet you have to hold tolerances that are in the microns, right? So a tolerance on a cathode, electrode, you might hold 4 microns of tolerance on that thing in your coating, okay? And yet it's moving at 50 meters a minute, okay? And a cell making, the tolerances you're holding like maybe 500 microns alignment tolerance between the cathode and anode in that jelly roll, and you can't even see it. It's moving so fast, right? So you have super short takt times, super tight tolerances, and you cannot rework anything, okay? Like, there is no rework, okay? If you put a defect in the electrode, you're gonna cut it out somewhere downstream, okay? If you don't make the cell right, you're scrapping it, okay? So you can make scrap at an enormous rate in a cell factory, okay? And the bigger the factory is, the more scrap you can make until you get it dialed in. So it is very tough to get a factory up, running, and profitable, because in your first year, you're likely going to make more scrap than you're going to gain in profit, right? And that's why it's so hard, right? And that's the thing. People think, oh, it's the chemistry, we're going to come up with this great chemistry, it's going to be amazing. You might come up with that great chemistry, but until you can manufacture it, it's about the manufacturing at scale, at speed, and being profitable. That's the trick, right? So just to give people finally some sense of like, what this looks like and what it can look like. So Sony, Sanyo, Panasonic all started making lithium-ion cells in the early 90s. To get to really big production, it was about 17 years, right? The Koreans started a bit later, okay? And they started about 1999. What they did, though, was they went and they hired all the people that were retiring out of the Japanese companies. And literally, this was a thing, okay? The Japanese had a mandatory retirement age. They still do. It was somewhere around 55 or 50 or 55. And, people finish working and they're like, oh, shit, I don't know what to do, right? And the Koreans came and said, come teach us how to make cells. And so all these super experienced Japanese engineers went to Korea and helped them make cells. And experience matters. They got it done in about 9 years, okay? So, experience really does matter. The Chinese did something similar. They got it done in about 6 years. That's how long it took CATL to become a giant cell producer. Now, Panasonic, for Tesla, first Panasonic was making cells in Japan, okay? They put a new factory in. It was about 2012. And by 2016, they were making about 60 million cells a month, okay, out of Japan. That was super fast. It took them about 4 years. We were commissioning new lines once a quarter, okay? And they were cranking on this thing, but they had a whole bunch of experienced cell makers to do it. And they had a lot of support from their government, okay? Like they were not running into permitting issues, I guarantee you, right? They were just cruising. Then, building the Gigafactory here too, really they started trying to make cells about 2016. And by, 2020, they were making, full capacity on that stuff, right? Which was painful because it was 4 years of like almost no profit, right? But it was pretty fast, okay? And again, experience matters, right? So that, and again, they had a lot of support, right? So, okay, what's next? People ask me about the next technologies. Is there something going to be better than lithium-ion? Oh my God, what happens if there's something better than lithium-ion? You spend all this money. Okay, there's nothing on the horizon that is that much better than lithium-ion. And if it is, it's going to take it a decade before it's ready, right? So, this people are like, what if it's something better? It's fine. It'll, the thing is, if you want to make something better, you need to make it at scale, which means you're going to make it on lithium-ion factory equipment. And so it's not going to matter. You can just convert your factory if you need to, right? Solid state, yeah, it's super the dream, but it's expensive and probably low volume. Sodium ion, it's the shiny new object, and I also feel it's like Chinese propaganda, right? The Chinese don't actually have a lithium source, okay? They don't, okay? They don't have a good lithium source. They're buying it all from elsewhere. And so they're hedging to make sure they can still make cells if they need to, if they can't buy enough lithium. So they're making sodium ion. And they're like, sodium ion's great. It is not great, okay? It is heavy. And then there's like a whole set of problems that people haven't explored yet, okay? Also, I have a close friend that ran Bedrock Materials. He was going to do sodium ion, and he and his partners tried this thing, and they modeled it, and they did all kinds of stuff. And they determined that it was never going to be economically feasible. And they gave the money back to investors and posted on LinkedIn about why sodium ion was not going to ever work, which made them really popular with the sodium ion community, okay? But, and then Natron was doing this for, a decade. They just declared last night they'll cease operations. They can't make it happen, right? I like lithium sulfur. That's what Lyten's doing, and I did it for the last 3 years because I think this one has the most promising of the new chemistries, but we were making damn sure that we could make this on lithium-ion conventional equipment so that it could roll into these factories and actually be made at scale in a reasonable amount of time, right? So I suspect that's still going to be the most likely new chemistry. It's a really challenging chemistry to work on. It's, you still do a lot of research to make lithium sulfur work, okay? And a lot of professors have tortured their students trying to make lithium sulfur work. It requires a really big team. I had 50 people working on this, and that's what it takes. It's not like 2 guys in a lab. They're not going to crack lithium sulfur, okay? You need all the team members. But if you want to know what's next, the best thing to do is to keep track and periodically pull down the Volta report. It's a crowdsourced report. It's the best industry research, and it's free. It's got all the topics about what people are doing, what kind of research they're doing, what kind of Factories are being proposed, who's doing what, who bought who. For the students, there's a salary survey in this thing that tells you what the typical mean salary is for the job you want to do. All of my staff use this, okay? So I use it, right? Very useful, right? So it's a good thing to get a look at. And then just, you know, the kind of key things I want to say, like electrification, it's inevitable. It's happening. Whether we in the US want to participate or not, the rest of the world is doing this thing, right? So we want to just keep that in mind. You know, batteries are the enabling thing. There's lots of stuff that's important, but if you don't have good batteries, you don't get to the levels of electrification that we want. And then, you know, just keep in mind that making cells is really tough. And, you know, I always warn people that humility is really important in cell making, okay? And this is another, you know, criticism. I've had friends that worked at Northvolt, and they're like, why did Northvolt fail? And they're like, well, there's many reasons. And I suspect there's a whole cloud of reasons why Northvolt failed. But one of the things was that, you know, the engineers were like, we're going to be better manufacturers than the folks in Asia. We know better. And it's like, you know, the folks in Asia have been making cells for 20 years. Maybe they know a few things. Maybe you should, like, take their advice. And they're all, no, we know how to do this better. They didn't take the advice. And they ended up with some really badly specified tools that are really tough to use. And then, you know, and the thing is, like, everyone has run into this. Like, the guys at Volkswagen, I heard him give a talk recently, and he said, yeah, we were arrogant. We thought this was going to be easy. And I'm like, wow, here's a German. Here's a German admitting on the world stage, wow, we were arrogant. And I'm like, wow, things didn't go so well, right? So it's really tough, right? So, you know, this is something that's going to be hard. You know, using the experience matters. If the government, you need to do this with a government agency because it's so difficult and there's so much money required. And then, you know, like I said, there's no easy shortcuts. Everyone like dreams of, I'm going to go in the lab and I'm going to make the next great technology. It's going to be super easy to build and it'll be awesome. Yeah, That next great technology, that was lead acid, okay, which people could make with a spatula, okay? That happened in the 1850s. Now you're talking about something that's way more high tech. You know, live with it. There's not going to be any shortcuts, okay? So, thank you.